Of a tour of the space and astronomy attractions that he came across in New Mexico. He's got some awesome pictures that he's taken. Some really nice imagery there, Rolf. So looking forward to that. Then we'll have our break, draw for our door prizes. We have a number of observations, and then Brian is going to talk to us about the RASC Observing Certificate programs. And Chris has got a number of things to talk to us about, including, as some of you may have noticed, the appearance of parking meters in the parking lot. So, yeah. So we're going to be asking if anybody has like really big hacksaws or bazookas or, yeah. But yeah, laser would do too. Yeah, but I'll let Chris address that one later. And needless to say, I hope nobody paid parking tonight, because we're going to do a revolt. All right. So what have we got? Our next one here is Ottawa Centre members in the news, and we do have a few this month. Beginning with Mr. Ledrew. Mr. Ledrew's got another article in the current issue of Sky News talking about star clusters that are visible at this time of the year. Good observing of some of these star clusters, and why they're there and why they won't be there always. So again, get your observing in while you can, because a few 100 million years from now, they'll all be gone. Nice article, by the way, there, Glenn, and the illustrations there. Where do you find the time, Glenn? Where do you find the time? All right. And also in the current issue of Sky News, there we have pictures of comet pan-stars down at the bottom from Pierre Martin. Some good coverage there of the comet there. I hope people got a chance to see it, because even though it is still visible now, it is certainly much diminished, as you'll see with some of the observations that we have. So, but it is still there. This might be one of your last good weekends to see it with a pair of binoculars or a telescope. All right, and another one from Pierre Martin, a beautiful shot of the Geminid meteor shower, and yeah, we drew out that quote from the magazine. I don't think Terry Dickinson is exaggerating when he calls Pierre one of the world's leading meteor shower photographers. So good work, Pierre. I don't know if you're here, but good work. Certainly, I've seen many photographs, images of meteor showers, and I can't think of anybody that does more spectacular work on those. So yeah, good stuff there, Pierre. All right. Oh, and that's it for members in the news. Gary Boyle.
Just to say he's not here.
He's not here. I don't know. Is he like you watching the hockey game or what? What's with that? Come on, Gary. Jeez. So I guess we'll see him next month there. So just as a reminder as well, we have a free lecture coming up, a public lecture by David Levy at the end of the month. We want to remind you of that at this meeting, obviously, because it'll all be done by the next meeting. A bit of a turnout there, so if you've got the time, and do they get a free parking pass?
Yes.
Yeah, a free parking pass. We're going to encourage the entire membership to become volunteers, and that way, when you're a volunteer, you get a free parking pass. That's one of the rebellious actions that we're contemplating. So, but we do need volunteers for this event. So if you've got some time on May 31st, please come up and see Chris during the break or afterwards. Much appreciated. Okay. And, oh, there we go from Mr. Levy. And up first is Al Scott with his Astronomy News Update. All yours, Al.
Thank you, Paul. So, a couple interesting news items for you this month. First on the agenda, water on Jupiter. ESA's, the European Space Agency's Herschel Space Observatory, has solved a long-standing mystery as to the origin of water in the upper atmosphere of Jupiter, finding conclusive evidence that it was delivered by the dramatic impact of comet Shoemaker-Levy 9 in July 1994. During that spectacular week-long collision, a string of 21 comet fragments pounded into the southern hemisphere of Jupiter, leaving dark scars in the planet's atmosphere that persisted for weeks. Now, our knowledge of water vapor in space basically started around 1995, when the European Space Agency launched its infrared space observatory, which had the sensitivity to get above the Earth's atmosphere, where all the water vapor blocks our view of water vapor outside the atmosphere. So we only discovered that there was water in Jupiter's atmosphere in 1995, a year after the comet had struck. It was widely speculated that the comet was the source, but there wasn't the resolution from that imager to tell. Scientists were able to exclude an internal source of this water in the upper stratosphere of Jupiter because there's a cold trap in the atmosphere that would freeze out any water vapor that would be rising, so that would fall back down. Thus, the water supposedly would have had to come from outside of Jupiter's atmosphere. Another possible source of the water would be a steady rain of small interplanetary dust particles into Jupiter, but in this case, the water would be uniformly distributed across the whole planet and should have filtered down also to lower altitudes. It would be possible that one of Jupiter's icy moons could be delivering water to the giant planet in a giant vapor torus, similar to Herschel has seen from Saturn's moon Enceladus. But this too has been ruled out. None of Jupiter's large moons is in the right place to deliver water solely to the southern hemisphere, as we see in this image here. So Herschel's observations found that there was 2 to 3 times more water in the southern hemisphere of Jupiter than the northern hemisphere, and most of it's concentrated around the sites of where those cometary bolides struck the atmosphere of Jupiter. So quite an interesting observation, and shows how, the dynamic nature of the solar system quite well.
When was this data collected? Is this very recent data?
I believe so. It was from the Herschel Hi-Fi heterodyne infrared spectrometer.
Interesting that after all these years, then, that there would still be that kind of degree of localization to the hemisphere when you're talking, approaching a couple decades now.
Yes, yeah, that is interesting. And you can see, the resolution isn't great from this spectrometer, but you can definitely see there's a south-north gradient. I'm also interested in why it appears that a lot of it is, very high altitude, like, even in the ionosphere of the planet. You would think if it got up into the magnetic field, it would quickly go around the planet. So interesting. Next. This is a news story regarding tiny grains of silica found in primitive meteorites. Silica, the chemical formula is silicon with 2 oxygen atoms, is the most common constituent of sand or rocks. And so it may not seem odd that small grains of rock have been found in a primitive rock, but it is, in this case, surprising because silica isn't one of the minerals that would condense, the scientists would expect to condense in the conditions that formed the meteorites. In fact, the scientists believe that these silica grains came from ancient stars and pre-exist the solar system. And the reason they think this is because they've measured the isotopic composition of these silica grains, and that is looking at the actual, using a probe, an atomic probe, they can tell whether the oxygen in the silica has a mass of 16 molecular units, or AMU, or 17 or 18. And everything in the solar system has roughly the same isotopic composition. Different stars have different proportions of isotopes amongst their atoms, but the material from our solar system was basically mixed and homogenized in the solar nebula that was formed. So all of the planets have a roughly similar isotopic mix. There are some small differences, but there are much larger differences between different stars. We can actually detect the ratio of isotopes in other stars by looking at the spectral lines that they emit. So we can tell that other stars have different isotopic ratios than our solar system. So all the planets in the sun have pretty much the same composition, and it's called solar, and these grains do not have solar isotopic compositions. 5 silica grains had been previously found before this month, but because their isotopic compositions enriched in oxygen-17, which is 8 protons and 9 neutrons, they were thought to originate from red giant stars as they blow off their outer atmospheres and create planetary nebulae. The silica, because of the chemical composition of these red giant stars, we think that these 5 grains that we had found previously were from some sort of a red giant nebula. The 2 grains that were found in this most recent study are oxygen-18 enriched. And this means that they are likely to have come from a core collapse supernova, which is really cool. A core collapse supernova comes from a very stratified star, and you actually have shells of different atoms inside the star. People have modeled the processes that form these atoms, and they know roughly the composition of these things. And the fact that they found oxygen-18 enriched isotopes suggests that these may have come from a supernova. These grains are too small to see with the naked eye. They find them with microscopes. But because the 2 grains which were found in 2 different meteorites have very similar isotopic compositions, the scientists speculate that they may have come from a single supernova, and perhaps the one whose explosion is thought to have triggered the formation of our own solar system. So quite an interesting discovery. And that's the end. Thank you.
Okay, Mr. O'Dale, come and talk to us about impact craters. There you go.
Yeah, they say geologists are also astronomers. We're only studying one planet at the present time. This image, let's make sure I get everything right here. Whoops, what did I do?
That's it, your talk's over.
Push the wrong button. Oh, I went to push that one. There we go. Yeah, okay. Double craters, Ritter and Sabine on the moon. If you take a look at it, this is in the southwest corner of the Tranquility Sea. If you were on the moon looking back at Earth, the Clearwater craters would be the exact same size as Ritter and Sabine look to us. So in other words, they're pretty well the same size. Just give you an idea of perspective. So tonight, the main theme is multiple impact craters, but I'm going to raise a lot of questions that I've been asking myself over the years, and a few people that have emailed me about questions as well that I can't answer. So just remember the Clearwater craters. We're going to get back to that in a little bit. Before I start, Oliver, are you here tonight? Yeah. Nice to meet you. We'll talk later. Okay, Oliver is one of the guys that I mentioned that emailed me about questions, and we're going to get into that particular question in a little while. So, let's see. Got it. Dactyl and, where are we here? Yeah, the dual asteroids here. Now, there's a paper, The Morphology and Population of Binary Asteroid Impact Craters. There's a paper about that was illustrating the type of impact craters that happen with binary asteroids. And getting back to the Clearwater craters, it is pretty obvious that it pretty well had to be a binary asteroid that impacted there. The dates are exactly the same with these impacts. We've dated them, uranium and lead dating. So it's conclusive that they happened at the same time. The chances of 2 independent asteroids impacting at the same point at the exact same time is pretty slim. So we pretty well assume that it is a binary asteroid. And the paper that I just quoted states that at least 15% of near-Earth asteroids are binary. So what kind of crater would a binary asteroid cause? Well, of course, the Clearwater is one example. The crater Hainzel, I think that's the way to pronounce it. This is Mike Wirth's picture. very elliptical. Now, I gave some talks about elliptical craters a while ago, and we hypothesized that they were from very low angle impacts. Well, this is a second hypothesis in the fact that of a double impact, you would get maybe an oval type crater, like one impact there and one right beside it. And over the years, erosion would cause it to be more oval. Well, what do we have on Earth that looks kind of like that? Well, Sudbury is a very good example. Now, I've mentioned this before. If you're ever worried about getting bonked on the head by a large meteorite, move to Sudbury, because there have been two major impacts there over the eons. Now, this is not a double impact. They are impacts at the same spot. Wanapatai is, 37 million years ago, and Sudbury, one of the oldest impact sites on this planet, is 1.8 billion years old. Now, up to this point, the hypothesis, the fact that the Sudbury igneous complex is very oval, the hypothesis is that at the point of the impact, this border here is the border between two continents that collided around 1.8 to 1.9 billion years ago, which had caused the Sudbury impact to have this oval shape. And the question I'm raising is, well, let's look at it. Could it have been a binary asteroid impact? Something to think about. That's one question to ask. And of course, my aerial photograph, you probably figured out by now that I like to fly over impact craters. The Sudbury impact, Sudbury igneous complex is this oval here. This is only maybe the 1/3 of it. And the Wanapatai crater in the background, just to give you an example of the relative size of them. I'm at about 2,500 to 3,000 feet at this point. But it's very, very obvious, the Sudbury igneous complex border right there. And in this area over here, I found many, many shattercorns. It's a paradise for geologists. So, next question. Around 470 million years ago, 450 million years ago, there was a major extinction, the Ordovician Silurian extinction event. It's the second biggest extinction event in this planet. At the time, there was only marine life and just the odd piece of plant life on the surface of the planet. But there is about a large percent, I don't know the exact percentage, but as I say, it was the second largest impact event on this planet. Now, there are a lot of suggestions of what happened, but one of the questions I'm raising now is that there are 4 craters here that are all dated, and of course every crater dating method has its error bar. 470 million years plus or minus 20 million years plus or minus 5, depending on the type of dating method you use, potassium, argon, argon, uranium, lead, etc. Every one has an error bar, but every one of these planets all fall in within those error bars, top, bottom, middle, but they're all within that error bar. So, one of the hypotheses that we can start is the fact that, there could have been a multiple impact on this continent that may have caused the Ordovician extinction. Not proved, not researched very deeply, but the paper that I'm quoting from is just recently in the last year. So the research has just started. So the craters, what do they look like? Well, 470 million years has done a real number on them. I'm starting from the bottom and work the way up. So I'll start from Oklahoma and work up to Lake Superior. The Oklahoma one, Ames, the data's right there, but it basically is buried. If you fly over it, there's just no indication that there's a crater there at all. But there's a lot of oil drilling. There's a lot of craters do happen to absorb a lot of petrochemical elements. And there is a lot of drilling in some of these craters, the ones in Manitoba and especially in the States. So from Oklahoma, we're going north to, this one is a crater that was just published just last year, Decorah in Iowa. About 4 years ago, geologists that were part of a survey team took a look at some water well drill cuttings, and they found some shock quartz. Planar deformation features in quartz is a very unique indicator of a large explosion. Two explosions that we know of that can cause these. One is a large impact, 12 kilometer per second bolide impacting the Earth, or a bit faster, or a nuclear explosion. So this happened 470 million years ago, dating, and chances of a nuclear explosion happening then was kind of slim. So we are fairly sure that this is an impact. Studies are going on right as we speak, but that is in the same date line as the Ordovician extinction. A bit further north, we're getting into Wisconsin, the Rock Elm crater. This is kind of a unique one. Again, there's lots of oil drilling here. The crater itself, it is a little bit visible. There's about an 80-meter dip where the crater is. It's kind of fine that way. It was unique, the studies happened in the fact that this was the worst soil in this farm area. Farmers here could not get anything to grow like a farmer out here could probably be getting maybe 100% or 50% more than anybody in here. It just wouldn't work. So they, the drilling did find planar deformation features, again in quartz, and with audio probing through the ground, they did discern the crater rims and so on. So this is the third crater in the row. 470 million years ago, as you can see, it did a number on it. It is not visible, but I did fly over it, and you can actually see the dip in the here. The crater just south of us, slipped my mind, but Eric and I drove through it, and it's a crater just north of Kingston, Holliford. And if you drive through it, people have been driving through it for 50, 100 years, and not even, it was just a hill. But again, finding a shape from an aerial photograph, they drilled it and did find planar deformation features which identified the crater. So Holliford and Rock Elm have a very similarity in that there is a slight dip there and the crater rim in the background.
We've flown over it also, Holliford.
Yes, yeah, we flew over it. We walked over it. One of the many craters Eric and I have survived through. We'll get into that in a minute. So, and finally, the fourth one in the Ordovician extinction was the Slate Island, the same date as the other three. This one, Eric and I did explore quite substantially through. We canoed from one end to the other, finding shatter cones and so on. This is an example of a piece of geology that if you find in the woods, it is unique to an impact or, again, a nuclear explosion. It's called a shatter cone, and I've shown, many examples of these at various meetings I've had. But this shatter cone on Slate Island is the largest one on this planet that's been discovered so far. For scale, that's me standing right there. Give you an idea how big that is. So that's going to be one of the expeditions from the GA this year, and I hope the weather's good for them, at least that they can find the shatter cone. If you ever get to Slate Island, the shatter cone is right behind that point right there. Just remember that if you have to go over there. But it is well worthwhile to see. It is, if you're any kind of a rock hound, it's a wow event.
We're going to do a presentation on it, Chuck.
Eventually, yeah. We have the video. Actually, one of the interesting things, Eric and I were, and his father, we were having breakfast on a picnic bench one morning, and about 5 feet behind me, this caribou walked behind us. The caribou herd on this island is the most southern herd on the planet. It was ice. They walked across the ice at one point and then were isolated. And since then, the many generations have evolved through, and they're very, very unshy of humans. You can't go right up to them, but they can walk by you if you stand still, no problem at all. This guy just walked by like, phew, another day. It's kind of cool. So Eric's got that on video. We're going to show it eventually. And of course, we saw lots of shatter cones on that island. So that's the hypothesis of those 4 craters. So we have another question to rise here. 200 million years ago, thereabouts, there were another series of impacts. And again, it could have been related to a late Jurassic impact event. And the craters that I'm going to show today are the Red Wing, St. Martin, and Manicouagan. Ron, are you here tonight? Ron St. Martin, Ron, he and I explored a couple of craters as well. And the St. Martin crater, I keep teasing, was named after him. But you can see there's kind of a line, a straight line of craters, some in Europe and 3 in Canada here. Dr. Spray brought this hypothesis up about 10, 15 years ago. The dating of these craters are very, very similar. The arrow bars, plus or minus 25 million years, 14 million, 3, etc., are pretty well constant. And the way the continents were 200 million years ago would pretty well stay that, hey, these guys are totally in line here. This is Rochefort in France now, Manicouagan, St. Martin, and Red Wing. I flew over Red Wing in the States. Again, it's full of drilling, lots of petrochemical resources coming out of it. And that's the outline of it. So just the thing, the crater's there, I have to fly over and take a picture. It's just, it has to, it's one of those things about an airplane geek and crater geek. St. Martin in Quebec, this is Lake Winnipeg. Lake Winnipegosis, Dauphin Lake. And right in here is the crater. A couple of things to mention about this one. It is one of the most pristine craters left on this planet. And why is that from 200 million years ago? Well, it happened in a very shallow ocean, and right after the impact, it was buried under almost half a kilometer or so of debris, and it's been like that ever since. So as we drill through it, you find a pristine crater wall, central peak, and so on. This is point 0 of it, by the way. There's a little town in there where the mine is, and I can't remember what they bury, what they get there. But one of the points I make, I call this Chuck's hypothesis. This is the Dauphin River. And the Dauphin River comes from the, what's this called? Right here. There's a lake here, and the river flows north, makes a 180-degree turn, and flows into Lake Winnipeg. Now the river, this is not a normal meander. A meander is a sine wave, like you see, goes up and down, back and forth, back and forth. This one here, the flow is from the south going north, makes a 180-degree turn and back, and then it follows almost a straight line to Lake Winnipeg. Coincidentally, the crater rim from St. Martin is right there. So the river comes north, makes a 180-degree turn, then follows the crater rim into Lake Winnipeg. I've brought this up with Dr. Oshinsky, and he's going to, he promised me he's going to look into it. You never know. But to my knowledge, nobody else has brought this point up, that this river here, the deviation is caused by the crater rim. On a previous presentation, I talked about the Chesapeake crater, and there are 2 rivers going into the Chesapeake crater that make a 90-degree turn right on the rim of that crater. So my hypothesis is that that's the same process that caused this diversion of that river. So that's another question rising up. The third crater in the row at the same time, the Manicouagan crater. Right there. Eric and I, we paddled our canoe.
That photo?
What's that?
Eric, and you flew over and took that photo?
Yeah, I got a super thermal on that one, I'll tell you.
Scared the crap out of me.
Yeah. I waved at Chris Hatfield as we went by. Actually, it was Chris in the shuttle that took this picture, coincidentally enough. Two things I want to mention. I mentioned this to Dr. Spray. One day I was daydreaming, thinking of the life of the universe and everything. I used this as my image on my computer. And I noticed this round event here, and Eric and I were investigating, actually exploring this to find out if it is in fact a crater or has any impact geology associated with it. Dr. Dentz, I asked him about this, and he specifically said, no, it's not a crater. It is just a geological anomaly. The circular lake here and the circular lake here are just coincidental. So two options there. One, it could be or couldn't be. When we, you never know. So something to put on the list for exploration in the future. But a couple of things. This is all impact melt. This is a cliff now. When the crater happened, of course, there was just a lake the size of almost Lake Ontario of impact melt lava. And as it hardened, basically it formed these cliffs, and we got lots of samples of that. But this one over here is very unique. There's a 10-meter bedrock, country rock that was ballistically blasted out from the crater by the impact and then went plop back into the lava and slowly sank. And as the impact melt lava was cooling, it solidified, and this rock sank and stopped right there. And this is a picture that Eric took. I didn't know about this until after the fact, and I'm very glad we got that one.
You're welcome.
Yes. It's Shattercone I picked up there, and this is a piece of breccia, and this is impact melt. Along that area that we explored was just a breccia paradise. It's all kinds of things. I like to, whenever I give a presentation at the museum and I talk to kids, I tell them, I'll tell you a story about this rock. It was sitting here 200 million years ago, minding its own business, and a big bolide happened, and boom, big explosion. Well, this rock was ballistically blasted straight up, and in the meantime, all the energy caused all the other rocks to either melt or vaporize. Then this rock came down from how many kilometers up in the air and went plop into the lava, and there it is. So that's the story of that rock. That's a piece of bedrock, and this is the impact melt around it. Very unique. It's kind of cool. Bedtime story for geologist kids. The rim around the Manicouagan, if you look at it, this is the trench around it. The picture I just showed you there is on that island there. And at this point, the wind, when we took off, we were heading back that night. It was nice and calm and cool, and we were in a canoe, of all things, full of rocks, paddling across about 15 kilometers here. And the wind was from the west. We're in the lee, so we thought, we get across, no problem. A little bit out, about a kilometer, 2 kilometers out, the wind veered to due north, coming right down the pipe here. And give you an example, there's the waves. That's an 18-foot canoe. Look at the size of that wave. We barely made it in there, I'll tell you. When more I think about it, we just dodged a bullet there. We were marooned on that island. We had enough food for another 5 days. Of course, lots of fresh water, so no problem. 2 o'clock in the morning, Eric shook my tent. Chuck, wake up, the wind's gone. Within 10 minutes, we're paddling like heck for the other side. We made it. So we were only there for, about 22 hours?
Yeah.
Something like that. It's a cool story, I'll tell you.
And if we'd waited another half hour, we'd be stuck another day.
Yeah, that's right, yeah. Because as we got almost to the other side, the wind came back up again. Yeah, that was cool. So here we were from totally marooned. 2 hours later, 3 hours later, we're having bacon and eggs at the restaurant. Surreal, I'll tell you. What can I say? So this is what the continents look like. This is the, so the first hypothesis was 4 impacts or 6 impacts, 2 in Europe and 1 in Asia and 3 in North America, may have been associated with the impact, the Triassic-Jurassic extinction. The other hypothesis, again, there was a large impact island, I guess it's called the Central Atlantic Magmic Province. And while the continents were splitting, Africa, South America, and North America were splitting at this point to create the Atlantic Ocean right along here. And there was a lot of volcanic activity. So, like there's 2 extinctions that had lots of volcanic activity. The one 250 million years ago, the main extinction, which was the Siberian Traps, large volcanic area there. The one that extincted the dinosaurs 65 million years ago. There's the Chicxulub crater that was coincidental with the Deccan Traps. That was another volcanic eruption in India. So here we are, we have the Triassic-Jurassic extinction with this large volcanic eruption again, plus the craters. So that's the question I'm saying, could the impacts have anything to do with these craters? Okay, so I'm back to Clearwater. And remember the dual asteroids, 15% of the near-Earth asteroids are binary asteroids. Clearwater Lakes, we're pretty sure that it was caused by a binary asteroid impact. So, hi Oliver. Oliver emailed me about a few anomalies just to the north of here. So this is what the continent looked like 290, almost 300 million years ago. When I flew over those craters, this is the crater rim between the 2 craters, west and east. So, Oliver mentioned that, look at these guys up here. Now, we don't know if they are impacts or not. This crater, I won't say crater, this structure here was investigated. Get my facts straight here. It's called Kaki. Well, I'll let you read it. There's no way I'm going to try to pronounce that. I'll quote the report here. A roughly circular lake averaging 6 kilometers in diameter in low relief Precambrian terrain. During a recent reconnaissance visit, several breccia boulders were recovered from the shoreline. The breccias are considered to be shock-produced, but exhibit a level of deformation slightly below that which distinctive shock features are formed. So it's just marginal. So the jury is still out. But the point that Oliver is making, whoops, where are we here? Could it have been a multiple impact? It could have, these plus these guys could have been the same impact event.
Sorry,
Now,
I'm missing 2 more saucers in that because Cactus Lake is really up north.
yeah, this is the Caddick Lake there. This is the one I think you were quoting, wasn't it? Or a couple down here?
There are 2 more by the left of that picture on the map.
Over here, you mean?
You can't see them on this image.
Oh, okay.
It should be at the left of Clearwater with that angle, but.
All right. I'm sorry, I didn't know that. I didn't realize they're there. Anyway, this is a thought. Could it have been a multiple impact event? As Oliver mentioned, there are other craters or other structures, circular structures around here that could be. So, we know that there's a lot of binary asteroids around. We know there's comets whizzing through back and forth. And just to give you an example that we are in a shooting gallery, this is the rings of Saturn with impact events on them. So it's even happening out there. So we are, as I say, in a shooting gallery. This is Hale Bopp. It was a big one. I think it was about 60 kilometers across. So if it had hit us, I don't know if we'd be around to talk about it. Anyway, I hope I raised some questions for you to think about, and thanks very much.
Question?
Yep, go ahead.
Could you go back to the Clearwater screen for a minute?
Sure can. Right there?
Yeah. Now, I'm going to put forward a hypothesis here.
Sure.
What if an object bounced, made a smaller crater, and there were shattered parts of it?
I don't know if the impact, like, it had to be a cosmic velocity to cause the large explosion. So in other words, you're looking at anything 12 kilometer-ish per second.
Well, the reason why I come up with this is because when I throw stones on the ground, as
Yeah.
a young child,
Mhm.
it would bounce.
Yeah.
And the second crater was smaller.
Yeah. The point I'm making is that if you're going at cosmic velocities, your first impact would be an explosion. It wouldn't be a bounce. So, people say, well, geez, every crater on the moon is round. Well, why could that be? Every impact was at 90 degrees? No. And unless it is a very, very low impact, 12 degrees or lower, you might get the bounce then. There are a couple of craters. There actually is one south of Sabine. I can't remember the name of it. Brian, maybe you can help me.
I think it's not the bounce that happens there when you get that one below 12 degrees. It's that when the energy is released, it's actually, I think, material sometimes
From the ejecta.
that goes.
Okay.
If you're throwing stones on the ground, there's no, the release of energy there is so infinitesimal that it counts for nothing. Coming in at 70 kilometers a second.
Yeah, you're looking at 12 kilometers to 70 kilometers a second. So yeah, as I mentioned, the first impact is an explosion. It isn't a bounce. So Brian's point, it's the ejecta that causes the impact events a little bit further off. Okay. Any other ones? Yeah, go ahead, sir.
Can you explain whether there's any relationship between the oil drilling that's going on in these places and the impact craters?
The oil drilling. Oh, yes. The question is, why is there oil drilling in the impact craters? The impact, that was the question? Yeah, the impact causes the large explosion. You get various damages as you go further away from the impact point. You get evaporation, melting, then rocks pulverizing, shattering, and then cracking, and so on. This causes a giant bowl. And over the years, what you got in the soil, in these rocks, fracking is actually showing you that there's a lot of petrochemicals in the rocks themselves. Well, this is like a giant frack. The oil does seep into these cracks within the breccia and the impact crater, and they pool there. And they, as these craters have shown, they're a gold mine for petrochemicals.
Chuck,
Yeah.
when you come back with your photographs, do you have any trouble trying to pick out where the actual crater was that when you saw it at the time? But do you have trouble kind of matching it up so you can put your circle on your image?
What I do, as you know, I'm a pilot, and we kind of like to know exactly where we are. I've never been lost in an airplane. There's a few times I didn't know where the airplane was, but that's another story. But to answer your question, now with GPS, I know ping exactly where it is. So I point the wing at it and take the picture, and that's where it is. Back in the old days, what I had to do was do the Latin long trick down to maybe a quarter of a kilometer, put a point on the paper map, and then fly over it and take the picture. So that's how I found out. When I did...
I used to use a sextant, of course.
Oh, yeah, of course you did, yeah. But you were in the ocean. You didn't have any landmarks. But yeah, basically, when I came over this guy, I knew the landmarks to look for. I knew where the center of the crater was in Bengal. That's what I did. Actually, a good point about that, when Jillian and I explored the Whitecourt crater, we stood in the middle and I pressed the GPS Find Me button to get the 6-figure Latin long. So when we flew over to take a picture, I couldn't see the crater at all. And basically what I did is I looked on the GPS where it was, aimed the wing at it, and took the picture. And sure enough, the crater was in the center after I looked at the picture on the ground. But from the air, we couldn't see it at all.
Have you thought about a bottom mounting camera on your plane?
Drill a hole in the airplane? Yeah, that's a good idea. No, I'm serious. We're looking into it. Eric and I are looking at all kinds of options, shall we say.
We want to mount a GoPro on the strut.
Yeah.
If I may now, there are some digital cameras that will print the exact location and the angle at which you took the picture.
Yeah.
Put
Yeah, it's amazing the technology, the price of things have gone down so much. Anybody else? Well, thanks very much.
Well, thanks, Chuck. Interesting as usual. Okay, 2-1 for Montreal with a minute to go in the second period. Latest update. Don't shoot me, I'm just the messenger. And Eric, about the photography there, you know, there's a second career waiting for you. You've ever heard of wing walking? I could see you doing that. All right. Well, thanks again, Chuck. That was interesting. All right, Rolf.
Okay, so this is a map of New Mexico. So we drove through New Mexico on our way to Arizona this winter, and we didn't have time to see all of these sites. It says at the bottom there, these are the New Mexico Space and Astronomy attractions. So there's a lot of them. The reason is partly because the sky is very clear there most of the time, and the population density is very low, so they can do a lot of rocketry stuff and blow things up, and not too many people will be hurt or anything. And a lot of secret stuff goes on there because there's not too many people around to see it, right? So anyway, I'm just going to highlight some of the things that we saw there. Felix Baumgartner, I don't know if you recall, back in November, he flew from a balloon at 128,000 feet to the Earth, and this was actually a demonstration of maybe recovering from damage in the spacecraft. You could maybe land with a parachute. I don't know. So that was so we drove by where Felix Baumgartner landed, and then there's a few other things there that we'll come across. Okay, this is it. This is where Felix Baumgartner landed, but you can see that it's very flat in many parts of New Mexico. No craters, but just on the other side of the road here, there were many oil wells, many oil rigs, because there's a lot. Every state has many oil drilling activities going on in it. So he landed in there, somewhere in there. This was a record that was broken, not since 1957 when Kittinger set the record previous to that. Now this is the town of Alamogordo looking down from a hill. This is the location of the Space Travel Museum, the Space Exploration Museum, and the what we're looking at there also is the Tombaugh IMAX Theater. There's two names that kept coming up throughout New Mexico, and that is Clyde Tombaugh, because he was very active in the Las Cruces area as a professor and, of course, the discoverer of Pluto. And by the way, in all of New Mexico, they still refer to Pluto as being the 9th planet. Other name that comes up quite frequently is Wernher von Braun, of course, associated with all the rocketry that took place in New Mexico. And this is the museum itself, and kind of on the top of a hill, and there are many displays of rockets and satellites in here.
Is there a V2 in there?
At
that museum? There
will be several V2s, yes. These are basically some of the manned satellites, and this is the Redstone that Alan Shepard took the first manned flight in for the U.S., and this is a Mercury capsule, Gemini and Apollo, and the space shuttle, and I believe this is a Soyuz, and also many unmanned satellites were on display here. For example, this one down here, does anybody recognize what this one is? That's Alouette. That's the first Canadian satellite. And I think these were a number of Explorer satellites. Most of this early satellites were named Explorer. There were many satellites named Explorer, I guess because that's what they did. Now, when you look out from that building and look down, you can see quite a few rocket artifacts. This is not an observatory as such, but it is a dome to protect the tracking cameras. This is called Igor, just like in Young Frankenstein, and it's spelled I-G-O-R. This is the V2 that was questioned, and there's a number of other rockets, and I won't be showing pictures of all of them.
What's the big white thing on the right picture? Looks like a part of a wing or something in the previous picture. To your right, it's like a fin or something.
This here?
Yeah.
Yeah, I forget what that is. Now, what was that? Do you remember, Linda? No, I don't remember what that was. I guess it wasn't that interesting. Okay, so this is a rocket called Little Joe, which you may have heard of. Anybody who is an aficionado of the space program knows what this is. And it's shown with an Apollo capsule on top. These were basically used to test the escape tower system, so the escape rocket. So they were launched up a short distance. I think they were solid fueled, and then this was used to test the fact that this could bring the capsule to safety in case there was any explosion of the lower part. There were other tourists there, and I thought that was very funny because they were dressed in black. Yes, now this is part of a V2. You know, when the Americans captured German scientists after World War II, they also captured about 60 V2s, and this is one of the remnants of one of the tests of the V2s. And it is the burned out bottom section, ironically located next to the only fire hydrant I saw. This is a Mercury capsule, an actual size, and you can go in, and it's actually surprisingly roomy, and Linda is there ready with her purse to go on her space flight. And by contrast, this is just the exhaust portion of the one of the 5 engines of a Saturn V rocket, and it's significantly larger than the Mercury capsule. Okay, and this is something called Sonic Wind number 1. This was used for testing. This is a rocket sled basically, and it was used for testing man's endurance for acceleration and deceleration. So it would be accelerated and decelerated, and you may have seen lots of videos of this. This is the Igor dome. There'll be some pictures of Igor later as well. Does anybody remember these experiments?
Yes.
So this is what I want. Remember that? This is Colonel John Stapp. This is actually called the Colonel John Stapp display or whatever it was of rockets. And he was a pioneer test subject who subjected himself to all kinds of these acceleration and deceleration experiments in the 50s. So we owe him a lot of information about space, preliminary space travel rigors that you'd have to endure. Also in New Mexico, the X Prize. Now, the X Prize was actually done, I believe, in California in the Mojave Desert. But the relationship here is that they kind of did the X Prize Cup, which is not just for a manned spacecraft, but for any kind of a space-related project that people want to submit to. So one place that we didn't go to see was Spaceport, USA, which was the spaceport that Richard Branson has built in New Mexico. Now, recently, Richard Branson had a successful flight of Spaceship Two, which is the suborbital spacecraft that he's going to be doing commercial flights with. The X Prize itself, I think, was won by Burt Rutan and Paul Allen on what was called, I think they call it Spaceship One. Spaceship Two, I think, is designed a little bit after that, in the image of that. So we didn't go to Spaceport USA. It was a little bit out of the way, and it's a little harder to get to. But that's in New Mexico as well, and I believe it's still under construction. Also in that building, they had the International Space Hall of Fame, and again, two names that picked out: Clyde Tombaugh, whose name, like I say, appeared everywhere in New Mexico, and of course, many scientists that worked on space and astronomy, rocket scientists like Wernher von Braun, and of course, astronauts, Mark Garneau. So he is honored here, but I guess not honored more than he's honored in Canada.
That's right.
Okay, so this is White Sands. This is not snow. This is sand. The very famous White Sands that the missile range is named after. This sand is all composed of gypsum, same as the drywall in your house, but this is just huge mounds of it. And it gets pretty hot, so they have these sheltered picnic table areas. These sands are always shifting, and the roads are not easy to follow there, and it's a little bit easy to get lost. So you have to kind of follow somebody else's tire marks to find your way around. Okay, so because of the white sands, not too much grows there, but apparently rockets grow. And yeah, this is what they call it, the White Sands Rocket Garden. This is on the White Sands Proving Grounds. So you need to sign in and go past a guard and everything to get in there. But well, they didn't charge for parking, at least. Many different rockets on display, and as you walk around these, you just are amazed by the fact that all of these many different kinds of rockets were designed and built for a special purpose. Like, it's just amazing, rockets to go 100 kilometers, 150 kilometers, 200 kilometers, 250 kilometers. So just amazing. Most of these, by the way, would be designed to hold nuclear warheads. So that's one of their purposes anyway. This is a device, I don't know if anybody would recognize this, but this was used this was the shroud that kind of covered the Viking lander, and this was a test vehicle for it, so they would use this to test its descent through the atmosphere. It's not a UFO. Okay, this is an actual V2, and this is actually one of the very few remaining actual V2s that are intact. It's been somewhat restored. So it's in a building now. It's protected because, as you saw from the other one, if you left them outside, they would rust. So they've tried to preserve this one of about 60 that they brought back and tried to put together and launch, and did a lot of tests on. And of course, the scientists came with it. Particularly Dr. Wernher von Braun. I was amazed at how big this thing is. You can see Linda standing there, and this was huge. This was a huge rocket. This is the Redstone. Now, the Redstone was designed by the same scientists after they came back to the U.S. for the Army, and it's basically the same rocket. It's scaled up about 50%, but the technology really has not changed much in about 70 years. It's fundamentally still the same liquid-fueled construction for most rockets. And this one was the one that was first used to launch an American into space. And I guess this one would also hold a nuclear warhead. Okay, lots of optics that were used to track missiles. So when you go through the White Sands Proving Ground, you'll see a lot of domes, and they would mostly hold tracking instruments like these, theodolites that would track the rockets and verify the flight. And ballistics is a very important field of study for the military, and that's what they would use to verify their trajectories with. And this is Igor, of which I spoke earlier, and a very large telescope, 35 millimeter camera attached to it, seat for the operator, and a telescope guide scope to track. So they would do very high altitude tracking with this camera. So probably a pretty good telescope too. Now this is a program. This is how they used to program computers. Rather than have keyboards to type in the program, you'd have to program the instructions basically with wires. So they'd have people putting together these wire arrays based on whatever program was written for it. Can you imagine? So they didn't do too much of that before they moved on to something else. Okay, so now we're just past the White Sands. You go over a hill, and then you see Las Cruces. Now, in New Mexico, there is an artist who paints all the water tanks, and this is one of the very interesting murals that he's put on, and it's obviously called the Space Murals Museum. And this depicts the Challenger crew, that the one that blew up, and there's others. This is Robert Goddard with one of his rockets, and the space shuttle, and there's a V2. So I'm not going to show the entire circumference. A collection of stuff that was being thrown out. So my people that worked at White Sands, they'd bring stuff home with them because it wouldn't be needed anymore, it would be in the garbage. And this is one of the things, the Space Station Freedom, which obviously Canada seemed to have been very prominently involved with. This was the forerunner to the ISS. I thought first this was the ISS, but it looked a little bit different. This was the forerunner called the Space Station Freedom. And all kinds of other artifacts. Very, very much worth a visit if you're ever in that area. Okay, now this is the very large array shown here in, surprisingly, one of the very compact configurations. They can move these on railroad tracks, move them further apart, but it's very unusual to see them this close together. This is, when they're closer together, the trade-off is that the resolution isn't as good, but the field of view can be much wider, and the signal-to-noise ratio for a particular image is much better. If they're further apart, you get better resolution, but you have to integrate a lot longer to get the image, and it's a much smaller field of view. There's 27 antennas. You have to get pretty far back, even when it's in its close configuration, to get all of them. I did count them. There are 27. There's a 28th as a spare somewhere. So I was looking at this picture later, and I noticed something here. So I just zoomed in on that image. So there's antelope playing there in the same field, and also Bugs Bunny down there, and I guess he took a wrong turn at Albuquerque. Okay, so that's it. May the 4th be with you.
Motoring right along. Okay, we're going to move right into. We're going to move right into our observation reports. As soon as we dim the lights here a little bit, we've got some nice stuff there.
You want that one off too?
If you can, yeah. Oh, there we go. Thank you. See, ask and you receive, right? There we go. Okay, first up, as always, Mr. Commission.
Okay, this is NGC 663. It's an open cluster in Cassiopeia, also known as Malot 11. 1 hour, 46 minutes, 61 degrees, 13 minutes, which means that it's circumpolar, so you can see it the year round here from Ottawa. The magnitude is 7.1, the size about 16 minutes, and the number of stars is 80 in this particular thing. The brightest star is 9th magnitude, and the distance is 6,400 light years away. I think this is pretty well the end of these small open clusters that I took with Glenn LeDrew as an experiment to see how the camera worked. I think when we start up again, we'll have something more interesting for you people.
Good stuff, Paul. Time to roll off that roof, right?
Yeah, time to roll.
Good. Thank you. Rolf?
So Saturn was in opposition on April 28th, and it's not a very good picture. Saturn is very low right now, and will be, I guess, for the next 5 years or so. And the seeing was horrible, but it was the first clear night in a very long time, and so that's it. Saturn at opposition. Hopefully there will be better chances coming up.
Thanks, Rolf. Isn't that upside down? Only kidding you. All right. Oh yes, I've got a few in here. Comet, as I mentioned, Comet Pan-STARRS. This is from about 2.5 weeks ago. Just becoming difficult to observe, certainly not naked eye anymore, but still visible through a good set of binoculars on a clear night, and certainly through small telescopes. It is dimming down pretty quickly, as you'll see in the next one here. This was only from a few days ago. Mind you, the conditions here were dismal. It was a hazy sky with a full moon up there, but managed to grab that with a Malin cam and stacking 15, 30-second exposures. Still can see the tail there. It's a bit of a fan there, but definitely nowhere near as spectacular as it was. So, as I say, if you want to try to get out this weekend and check it out, this may be your last opportunity. All right, then I've got a couple of interesting ones here of the moon. The area that I'm looking at is within the rectangle here, and it's one of my favorite areas to do observing, and there's a number of really very cool features in this area. Down here we have Kepler crater with splendid ray formation from the ejecta, and a couple of my favorite areas here. This is of course, Aristarchus with Schroeder's Valley here, and the plateau. And this is an area that I've been trying to bag a half-decent image of for quite a while, called the Marius Hills. Anyway, I'll have a look at each of these. This is from about a week ago, and crater Aristarchus, they're about 41 kilometers or so across. This is sitting in what's called the Aristarchus Plateau. You can see this is a raised region above the Ocean of Storms Mare floor. This plateau extends up to about 2 kilometers in height above the Mare floor, and it's chock full of volcanic related features, such as Schroeder's Valley here, which is believed to have carried significant amounts of lava when it formed. Aristarchus is the brightest crater feature visible on the near side of the moon, on our side of the moon, and the reason for that is that it's a very young feature. As features on the moon go, they estimate that impacted on the moon about 450 million years ago. So rather interesting feature. Just south of that is the Marius Hills. Now, this is an area that's always fascinated me. If you're having problems with the perspective here, you can see the craters are lit on the sort of the upside, if you will, and shadowed on their lower side, whereas it's reversed on the hills there. So you can see that this entire area, this is the crater Marius. This entire area here is pocked full of these volcanic zits, if you will, for lack of a better term. These are volcanic domes. This is the highest concentration of volcanic domes and related features anywhere on the moon. And it was also considered as a potential landing site for one of the Apollo missions that was subsequently canceled by Tricky Dick back in the early 70s. This is a really an interesting area. These domes are relatively low. I don't think there's any of them more than about 1 kilometer or so in height. And when the Terminator is even a little bit lower than when I captured this last week, the shadows are quite dramatic there. But typically the domes are more on the order of 0.5 kilometer or so across. So you can only really see this and image this a couple of times during the month. If the sky is clear and of course if the moon is up in the evening, it's because they're such shallow features there. You lose them pretty much when the Terminator is not close by, either on one side or the other. So just to give you a sense of scale here, again, this is the crater Marius, for which the region is named. It, again, is about 41 kilometers across. The smallest features that you can see in this particular image are about 2 kilometers across. You can see there's a small crater there inside Marius. That's about 3.5 kilometers across. There's a very small one there, about 2 kilometers across. So just to give you an idea of the size of what you're looking at. So you could probably fit most of Ottawa within that crater. Yes, the whole area is full of these volcanically related features there. So it's crisscrossed by rills, and you've got the volcanic domes. And interestingly enough, the rill that you mentioned, one of the reasons I wanted to image this is a relatively recent discovery, and that's the Marius Hole or the Marius Pit. Now, we have talked about that just recently, a few months back. But I wanted to show you this because this is there's been some updated imagery from the Lunar Reconnaissance Orbiter, and this Marius Pit is a very cool formation. It's basically a hole in the ground. It's not a crater. It appears to be a hole, and the speculation is that it is part of the roof of a rill, a lava tube. That has collapsed downwards, and so basically it's a skylight opening up into the rill below. This was first discovered by the Japanese Selene spacecraft a few years ago through imagery. You can see the area here in the Marius Hills region there, and a higher resolution view. This pit's only about 65 or 70 meters across, and I thought we'd show you that animation there. Chris, if you want to roll that. Talk about a needle in a haystack. Watch this. This is created from the Selene imagery. So Selene had a couple of very high definition, high resolution video cameras on board, and did a lot of high-scale fine definition mapping there, as I've shown you in the past. And you can see the number of rills here. Again, where these are remnants of old lava tubes. Take a note of that right there. That pit, or that opening, appears to be right at the bend of that old lava tube. But talk about a needle in a haystack, right? So what they did, when this was recognized, what they did is NASA targeted the Lunar Reconnaissance Orbiter, which had even higher resolution cameras available, to take some images of this formation. And this is a shot from basically directly overhead, and obviously the pit floor is in shadow. And what they did is they took a number of images over a number of different orbital passes where the inclination, the solar inclination, and the orientation of the orbiter with respect to the hole itself was different, because they were trying to get it so that they could see into the bottom of this pit, and if it is a collapsed feature there, to see if they could see even beyond the rim down below. So again, this is a high resolution view taken directly above. You can see that it's unlike a crater, which tends to have more shallowed walls. This looks like basically like a hole you would drill with a drill bit. And obviously there's boulder debris on the bottom here, and it is. It's very much like a sinkhole. Remember the Queensway, right? So there we go. Only this one's a little bit bigger. As I say, it's about 65, 70 meters across. So what they tried to do is they did some calculations when the orbiter would pass at different angles under different levels of illumination, because they're trying to see if there is. We don't know right now whether this is an opening to a vast underground cavern, if that rill is hollow underneath a layered roof, or whether it's basically just a sinkhole and it just drops down. So they're trying to image beyond the rim there with these, and basically they've got this so far, which is really kind of cool. What you can see here is that it definitely looks like there is some subsurface featuring there. The mantle itself appears to be, this is really interesting, because the mantle itself appears to be, about 30 or 40 meters thick on top of this, with striations, layers of material. They speculate that this is different periods of lava flooding in this area that built up these layers gradually. It's an interesting feature intrinsically, but one of the things that they're contemplating, and why there is such interest in this, is that this would be probably, if this extends some of these things, so they could extend literally tens or maybe even hundreds of kilometers under the surface. But if we're talking about long-term exploration and colonization of the moon is a harsh environment. You want to have something pretty substantial shielding you from things like coronal mass ejections from the sun and other nasty things like that. We're protected here on Earth because of our complex fields and the magnetism here, but on the moon, if you get a burst like that, you want to be indoors and you want to have something substantial over your head. So these are proposed that if these are stable and if they are in fact caves, that these would be ideal places for future colonization. So just want to... A water trap?
Yeah, you get water condensing on the sides of craters that are not exposed to the sun. A small amount of water vapor moving around, like get in there where there's no sun, it's very cold.
You could freeze out. Well, interesting thought. Anyway, so that's the latest on that. We've discovered about I think about 4 of these pits on the moon, and interestingly on Mars as well. So, all right, that's all I have for you today. There we go. Thank you. And up next is Mr. Peterson. No, it's not.
Yes, it is. Okay, it's the night for the moon, though, I guess. Okay, so after a few years of playing it safe with deep sky imagery, I decided to start doing some hard stuff that is planetary. I picked up one of these Celestron cameras, and so far I've only put it on my 6-inch refractor with a 2x power mate. The first thing I pointed out was Jupiter, which was hanging like low fruit in the sky. I didn't expect very good results. We're way past opposition, way past transit, and seeing was pretty bad. Plus, I didn't know how to use the camera, really, so this is the result that I got. Whoa! No, it was a lot better than that. Okay, so that didn't come through very well. Well, we'll skip that then. There we go. That's what it was like after processing. Okay. This is really quite funny to look at. It's all green and stretched, but anyway. And so then I expanded the size of the chip, and I was able to get a couple more moons, Europa and Ganymede, and so that's not too bad for, I think, a first attempt with the camera. Like Rolf, I went for Saturn. This was about a week before he did, though, I think. Yes. And yeah, so I put 3 videos together for a total of about 6,000 frames, and this is actually a lie. It's not the best not the best 10%. I think I actually used 15% for a total of 900 frames. I had quite good seeing, and hopefully I'm going to try to get it tonight with my 11 inch, just if I can do a little better. So it's not too bad an image. You can see the faint C ring in this one, and the bright areas on either side of the Cassini division are real. Those are not artifacts of processing. At this point, I think I might have set myself up for embarrassment, because, Rolf, your image was upside down from this. Is the North Pole of Saturn visible now, or is that the South Pole? I thought it was the North Pole. Yeah, good, okay. All right then, so I can use this next slide. For those of you who missed it, that's the real picture by Cassini of the North Pole. One of the strangest things in the solar system, surely. Okay, so a few hours before I did Saturn, I was practicing on the moon, and I had quite a bit of time, so I've made this composite of the Terminator. And you can see all the numbers on there, 10.8 days old. And I'd like to focus on, especially on Gassendi crater. Tonight we'll take a closer look at that. But before I show you that, a quick look at Plato, just because there's something there that indicates the extent of what I could probably photograph with this setup. There is, as everybody I'm sure knows, a central rill inside this Graben Valles Alpes, which is often used as an observing challenge. Was just barely able to image parts of it. Although the light is bad here, I could do better, I think, if it was closer to the Terminator. But that's just an excuse to put up a picture of Plato, isn't it?
What's your shutter speed?
It would be fast for the moon, I think about 1/125th of a second. I didn't anticipate that question. And about twice that for planets, I think.
Yeah, that one I was curious.
Yeah. Okay, so Gassendi crater. Like most imagers, I don't really know much about the moon. Although I am a geologist, I haven't paid that much attention to it. It turns out I picked this picture because it was close to the Terminator, and it turned out rather well. But it turns out that Gassendi is actually one of the more interesting craters on the moon. It's thought to be about 3.6 billion years old, rather on the old side for craters. It's on the north edge of Mare Humorum, which is a funny name meaning wet or moist, I suppose. It's named after Pierre Gassendi, who was a French philosopher, mathematician, astronomer. He was the first person to observe a transit of a planet across the face of the sun. That was Mercury, and that was based on a prediction by Kepler. So a fruitful get-together of those two. Now, the central peak of Gassendi is 1,000 meters. Spectral analysis of reflected light indicates that those peaks on the rough crater material around it consists of different types of gabbros, troctolite, norite. If you don't know what those are, they're exciting to enigma petrologists like me. They're iron and magnesium-rich rocks, essentially the same composition as basalt, but they are terms that are reserved for coarse-grained rocks, plutonic rocks that crystallize at some depth. And so I was unable to determine really if these are excavated deep rocks on the floor of this crater, or if they are in fact just compositional terms for volcanic rocks. The rills that you see here, whoops, that was a big mistake. So the rills that you see are usually thought to be related to volcanic tubes, as Paul was just saying, but they can also be a result of extension due to local subsidence, and there has been quite a bit of that actually around Gassendi, and so I'll just quickly go over that story. The scarps that you see in Mare Humorum here, you might want to think are the edges of basalt flows. That's not the case, as I'll show in detail in a moment. And you will notice that the south edge of Gassendi, lavas have leaked across this crater rim here, which has tilted to the south, so the lavas could flow into it. And the thinking is that gradual filling of the mare resulted in subsidence, which pushed down the center of the mare and tilted the crater so that lavas could fit in there. And so I found this paper online. Hackwell et al., they mapped the composition of these lavas by spectral analysis, they're able to come up with rough ideas of titanium and iron concentrations. I was unable to overlay their map precisely on my image here because they're completely different projections, but these green lines give you an idea of how they match up with each other. And they also estimated the ages of the flows using crater density. And so this is the sequence of infilling of Mare Humorum that they came up with. So at 3.5 billion years, so that's 100 million years after the formation of the crater itself, the first infilling. This 7.5% here refers to the amount of TiO2, titanium dioxide, in the basalt. That's a horrendously high concentration, far beyond what you'd see in any basalt here on Earth. You may remember a few months ago I gave a brief talk about armalcolite, magnesium titanium oxide, a very rare mineral on Earth, but it's very common on the Moon. It's compositional differences like that that make for that unusual mineralogy of lunar basalts. And so then that was followed up at 100 million years later at 3.4 billion years. So as you can see, this is a very long, it's not a single event, but these things get filled. This took quite a while. This is presumably the one that partially filled in Gassendi. They were unable to determine the ages of these small units here, I presume because they didn't have enough, good enough statistics on the craters. And the final one there at 2.79. I couldn't be bothered drafting all the stuff that was up here. So that's Gassendi and Humorum.
Great. Thanks, Tony. Nice imagery. All right. Last but not least.
While you wait for him,
Hmm?
all over 3-1.
It's all over? Yeah? 3-1, it's all over, I'm told.
You did right by coming here.
Yeah, see? You just would have been ticked off if you'd stayed at home and watched, right? All right, Brian, where are you? There you are. Brian's going to talk to us about the various observing programs and certificates available through the RASC.
Right.
There you go, sir.
Sorry. Thank you, Paul. During the break, young Julia and I were talking about why it is that people come together at meetings like this. And I think we're seeing the evidence of it, especially in these last few presentations, especially in the observation reports, really excellent observation reports that we're getting. When somebody like Paul Commission takes an image of a star cluster, he can take an image and you can throw it in your observing bag. You've got that one. Move on to the next one. But you notice what Paul does. He finds out, well, what is going on with that cluster? He knows he knows exactly where it is, what constellation it's in a sense, how it's situated in our observable universe. He talks about the distance to it. And to me, when you're talking about deep sky objects, especially, the distance factor. Is something that really resonates with me because it's a chance for you to stretch your mind to, well, what are we seeing on the path toward that object? Whoops, I'll just move that out of the way. On the lunar images, do we have the full moon image that Paul showed, please?
Way back.
Way back, yeah. When Paul Cloninger showed his full moon image, I mean, you can go and take a nice shot of a moon like that. Right, but it's when we zero in, like Tony just did with looking at Gassendi, the crater Gassendi, right? So you're now starting to get a bit more particular information about a certain area of the moon. So it's easy to be, I think I've talked about this before, it's easy to be a tourist with your astronomy, and that's fine too. But if you're looking for something, if you're kind of maybe getting tired of just doing the touristy things, for the Royal Astronomical Society, the national office has observing programs for various aspects of astronomy. One of them, of course, is the Isabel Williamson Lunar Observing Program. And Chris, no, that's okay for a second. How many people did you say have completed that?
In Canada, 14 people.
14 people in Canada have completed this program that's been on the go for at least 4 or 5 years now.
Since 2006.
Since 2006. All right, they're thinking that maybe it might be too difficult to program, but in the case of the Isabel Williamson program, and we saw the patches that were up there a few minutes ago, but it's a great program because when I get some clear time starting in June, I'm going to be, my notebooks are full, just full of lunar observations. I'm going to start gathering that, and I'm going to put it all together to complete my my Isabel Williamson Lunar Certificate program. And it walks you through. It takes you, well, it looks at the moon as a whole object. It says, now let's look at the large structures that we're seeing there. Now what structures on the moon occurred to change the face of the moon? And they start walking you through everything. And if you're looking for something that's really satisfying to do, it's when you go and say, I'm going to look at the moon tonight. But the reason, well, Tony, you were just saying you're going to be going after Gassendi again. When you're going after a specific target, suddenly you'll find you're super focused on what you're doing. You're going to maybe do a bit of background reading on what it is you're going to be observing, and that's when you get the most out of it. So when you can put it all together and you can share it with other people, the object in a sense becomes yours in a very, very personal way. When I met Clyde Tombaugh in 1989, he was doing his Tombaugh Scholars Program tour across Canada. So he went across all the Royal Astronomical sites in Canada and gave lectures. Now, this was my very first year in the RASC. So I had joined in the summer, I guess it was, and he showed up in September or October. And he gave his presentation about how he discovered Pluto. It's a fascinating story. I may tell that again in how it relates to me, because that pushed me to go hunting for Pluto myself. And at the end of the lecture, well, actually at the end of the lecture, I had my observer's handbook with the cover torn off. Art Fraser, you gave me that at that very first meeting I'd gone to. And I flipped it open, I flipped that observer's handbook open to the Pluto Finder chart for 1989. And I went up to Clyde Tombaugh and I said, Mr. Tombaugh, would you mind signing my observer's handbook, please? And I had the Pluto Finder chart open. And he looked at that, and he looked at me, he says, no one's ever asked me to do that before. I thought, well, this is great. So I've got a signature in my book, but that signature there, that pushed me to go hunting for Pluto myself. And in 2001, I'd have a number of false starts trying to find this little rock orbiting the sun. And in 2001, I made it a focused study to go after that. And I was eventually successful. And across 3 nights, I think it was in June or July of 2001, I was able to make a sketch and plot Pluto's movement across the background stars. Now, when we go to if we can go to the certificates in, please, Chris. When they show the various certificates that are available for observing in the Royal Astronomical Society of Canada, I mean, it's choose your poison there, right? Choose your play pal. Oops. Oops. I forget what year it was. I think maybe '96 or something. I got my Messier certificate. Now that's something I'd been poking away at, because when I joined the RASC, people talked about this Messier certificate. This Messier certificate you couldn't be an astronomer unless you did your Messier. Okay. And I started going after it. And what it was is the number of interesting objects in the sky that the French comet hunter Charles Messier had been noting. In fact, he was looking for comets, and then he'd look in his eyepiece and he'd see this, it was actually a galaxy or a nebula. He'd just, it's not a comet. So he'd mark that down as part of his list of rejects. Well, tough on him, but his list of rejects is what we know as the Messier list, pretty much. And so it's a great thing. And what it does is, by following a focused program of study, you learn the sky. And I'm telling you, you are going to understand a new ownership of your own hobby of astronomy by doing something like that. You move up a step, go to some of the deeper sky objects, the finest NGC objects from the New General Catalog. Rick, you've done yours, have you? Yes. Okay, who else has done their finest NGCs here?
It's coming on a slide.
Okay, John, you've done yours? Fantastic. Oh, it is, okay. I mean, to move up to a level like that, now people have done maybe the basic levels they've gone to now, a much more challenging list of observations. And the more you challenge yourself, the more you're going to get out of it. What was that the Beatles said? The love you take is equal to the love you make. This is what the story is right here. And Explore the Universe, very basic entry-level type of observing program. And I urge, I mean, you can go online to the national site, and it has all the descriptions there. You can download the all the observing forms that are required for the various programs. It's wonderful. It's wonderful. And if you have the opportunity to do it, I really urge you to take a closer look at maybe doing something like this. And I think, are we going to be talking at some point about there's the national office is the one that authenticates the certificate. So you send in your observing reports to the national office, and they approve the certification. But I think it would be a good thing if the Ottawa Centre was approached, I think back when I was meeting chair, about possibly, because we got such a, I mean, look at the talent we've got in our club here. We have 400 and something members. The talent just that we have in this room alone is unbelievable. We could, I think, make an application to become a certification centre to take some of the strain off the national office for handling people's observing logs and checking them out and authorizing certificates. So, anybody have any questions about any of the programs that are on there? I mean, you're gonna find out much more just by going online and reading it for yourself. Paul.
Ryan, there are 7,840 objects in the NGC catalog, another 5,300 in the IC catalog. There's over 13,000 objects. I've seen 2,000, just over 2,000. If I wanted to see them all, I'd have to live to be 200 years old. So you'll never run out of stuff.
Yeah, and I think I kind of hit a wall within a couple of years, maybe 5 or 6 years into my membership in the RASC, because I was kind of looking at this, looking at that, looking at this, and I kind of had done it all. All right.
Sorry, these slides are clipped at the top, but the list on the right are the Ottawa members that have achieved these certificates that are posted on the website. I'm sure there's lots more before this 1994 when the RASC started posting them. And there's the big gaping hole.
Somebody want to beat me to that one?
How many you got left to do, Brian?
I don't know, I have to get all my notes together. That's the one part.
Okay, there's a challenge, right? There's a challenge for you. Beat Brian to the punch. All right, thanks for the review on that, Brian. And Chris, you've got a few items that you wanted to address.
You got a beeper here?
There you go.
Yeah, a few announcements before we get to the closing slides. First of all, a thank you to those members who volunteered and helped out for International Astronomy Day. We do this every year here at the museum. We try to have 3 different events, an indoor event within the front lobby of the museum, which you'll see in these pictures that should be passing through here. We always have, or we try to have solar observing outside. Who would have guessed that on April the 20th, we had not just clouds, but snowstorms. So we weren't able to do that during the day or the evening. So again, a thank you to those members who volunteer here at the museum. And as the next slide we'll talk about, they will be rewarded for their efforts. You've heard references tonight, and I wonder how many people had noticed this until they heard it tonight, but some bad news here at the museum. The museum, the 3 science museums in Ottawa have just invoked parking fees. They're already in place. If you were observant when you arrived here tonight, you would have seen a parking meter, a pay meter, and if you did not pay, you may go back tonight and find a warning on your car. Next month, it won't be a warning. It'll cost. Of course, that's a real shock to us here at the club in that we put a lot of work in helping the museum. We get a fantastic deal for renting these facilities in return for providing our services. But I have real fears of what imposing a parking fee might do on people's willingness to come to meetings and stay as a member of the club. So certainly council and myself and Gary have already expressed our views to the museum, and we'll keep you up to date with whether we have any success on bending those rules for groups like this that give a lot of service back to the museum and are only here at night. But in the meantime, from here on in, you will have to pay for parking on the museum property, unless you're one of the volunteers that have been helping here at the museum and have received security clearance. In return for that clearance, there's a parking pass waiting for you at the front door. And I know most of you tonight that I've seen have already picked up that pass and have it on your windshield. So there's a benefit to pay. Don't flood me with 200 applications for volunteers. It's one way around the system, maybe. Not until we work with the museum more, but we'll see what we can do. In the meantime, here's some hints for you. Here's an aerial photograph of the museum. Here's the museum on the right, the grounds in the front, the famous lighthouse in the front. That whole street. Lots of parking on the full length of the street, both shoulders, no meters, and a very short walk across the front lawn to the museum. But a warning, Lancaster Road, it's not only no parking, I should have changed that slide to say no stopping. So I think a rather expensive one if you were to try to park there and come in for the evening. There are other solutions around there which I'm not going to bring to your attention. You may figure them out. I don't think they're quite kosher, but there are certainly other parking areas in the neighborhood. So volunteer and you're free. Short walk from Gladwin Crescent free. Otherwise $6 at the pay meter. And last, I wanted to talk briefly about an old system we've had in place. We usually refer to it as the mem list, or the members' email distribution list. It's not been heavily used recently, and we've discovered to our surprise that the maintenance of that list has fallen badly behind, and we've just fixed that. So this is a service we provide to all our members where if we have your consent, your email address is put onto the members' mailing list, and then anyone who wants to send an email to that long, complicated address gets to speak to all the members. You don't really need to remember that long address. So once you're on the list and receive emails, you'll quickly know what that address is and can use it over again. There were simpler addresses in the past that were used, which are no longer valid, and I hope we can get them back in place, but in the meantime, that's the only way. So there's 2 ways to get on that list. You can either send me or one of us in council an email and ask to be on the list, or we recently put in place a new system online so that when you renew your membership with RASC through the national office, from here on in, there will be a tick box at the end saying, would you like your name added to the email list? And then on a monthly basis now, I'll be monitoring those tick boxes and adding you to the list. Art raised an interesting fear tonight, and that is if you do this once but don't do it every year, that may mean you come back off the list. I have to figure out how that works. But in the meantime, a great way to communicate amongst members. Fortunately, this site I find does not get any junk mail, does not get a lot of repetitive or uninteresting emails. It's only used for, I think, really interesting messages and really worthwhile joining it. There is a similar list for Flow members. It hasn't been maintained recently, and we're trying to figure out how to get back onto that one and fix it. And another list I'm hoping to work on that announces to people of our public star parties. But in the meantime, if you want to be on the members' mailing list, let me know, or on your renewal, take note of that tick box and give us your consent. And back to Paul for the final announcements.
Great, thank you. All right. I've got a couple of miscellaneous pieces there as well. Eric, you wanted 30 seconds? Tick, tick, clock's running. Tick, 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 tick.
As you know, we're recording the presentations, and now I'm excited to let you know that they're also available online. So if you have a presentation that you'd like to publish, contact Chuck. Several members have already given the green light to automatically present their presentations. Chuck creates a link on the RASC website, and then the video is actually coming from YouTube. So the 10-minute astronomy update, Simon Hanmer's presentations, Chuck's, mine, and a few others are available already on the website. So please, I encourage you, let's show the world. Thank you.
Excellent.
Is that 30 seconds?
I think a bit more, but it was worth it, so good stuff. Good work, Eric. All right, another thing that just came to my attention earlier in the meeting, I don't know, for those of you that were here last month, you saw a homemade telescope made out of, amongst other bits and pieces, drum bodies. Now, a gentleman has come forth and said that he may be able to get some drum bodies of various sizes for people that might be interested in doing something similar. Or one of the things I thought about was perhaps even as as a sort of a framework for a solar filter, that type of thing. If you're at all interested in that, let me know or let Chris know. We'll take names there, and the gentleman will. And I'm sorry, sir, I forgot your name. Mark, there you go. Mark is going to look in to see the availability of these to see if we can get them. So something to keep in mind, and let us know if you're interested. Again, on a similar note, we're also still making available or considering the stone pillars that Tony talked to us about a few months ago there. So again, if you've got some interest along those lines, contact myself or talk to Tony. All right, last few slides, Estelle's pick of the month, the 4% universe, dark matter, dark energy, and the race to discover the rest of reality. So apparently that's a good read. So thank you, Estelle. As usual, we have our post-meeting entertainment across the road there. We have Al Scott here, and you can talk to him about the equipment library. Art and Ann Fraser are obviously here, and the rest of the museum is closed, as usual. So our audience tonight, a little on the light side, probably because of the hockey game, 95. See, they should have come, huh? They should have come. Thanks to those that took the time to put together presentations and observations, and to our host, the Museum of Science and Tech, even though we don't agree with their parking policy. I had to get that in, I'm sorry. Complaints and comments, just send me an email. I wanted to remind you, too, that our next meeting is June the 7th, also a swap table day, right? One of two that we hold every year there. So swap table will be going on next meeting, June the 7th, and we hope to see you all there. Bring a lot of good stuff there, and in the meantime, clear skies, good observing, and be safe. Take care, and good night.